Okay, so zero eigenvalues. Why these cases are special and different when you look at the picture compared to other cases. One thing to keep in mind though, in terms of solving the systems, the fact that lambda is zero doesn't make any difference with the formula sheet. You just apply those three cases. It doesn't matter if one of the eigenvalues or both of them are zero. So the algorithm of solving the system is the same. Notice here that, take a moment to write this down, but this is an example when you have a zero eigenvalue and a positive one, a strictly positive one. Formula for the solution is this first case, when you have distinct real eigenvalues. One combination, v1 e to the lambda 1t, v2 e to the lambda 2t. Because one of them is zero, that's why there is no e right here. Okay, so this would have been the place of e to the 0t. e to 0t is 1, so therefore the solution looks like that with exponential attached only to one eigenvector. So the formula for the solution doesn't make any difference. The geometry of solutions is quite different. Now, why that's the case? Well, think about for a moment how the matrix of the system looks like in this case. So when you actually solve for these eigenvalues, for one eigenvalue to be zero, you need the determinant of the matrix to be zero. So, when you set up your characteristic equation, is lambda squared minus the trace, which is 4 lambda, plus the determinant, but the determinant is 4 minus 4, which is 0. So only if the determinant is equal to 0, then you would have 1 or 2 zero eigenvalues. Because only in that case you could pull out lambda, and it's one of the factors in the characteristic equation, so therefore you have one zero eigenvalue. But what does it mean from a linear algebra perspective, the fact that the determinant of the original matrix of the system is 0? Well, it means, first of all, that the equations themselves are dependent. Okay, so notice that the rows in the matrix, which represent the ODE themselves, I wrote here the system in components, these are dependent, which means that one equation is a multiple of the other. So notice I can pull out the factor 2 from the second equation, and you get the first equation on the right hand side. So right off the bat, you have a major change with respect to what's the equilibrium point. Well, because the equilibrium point is given by, when you set both derivatives equal to 0, you don't get a single point, the origin. You get an entire line. Okay, so you have infinitely many solutions of this system. 2x plus y equals 0, this doesn't give you anything new. Okay, so any point on the line, let's write it down here, so any point on the line 2x plus y equals 0 is an equilibrium point. So therefore, in the zero eigenvalue case, we have what is called a line of equilibria. If you start on that line, there is no motion. Anywhere when you start on that line, there's no motion. You get stuck there because both derivatives are 0. And that line of equilibria is the eigenvector corresponding to to the eigenvalue equals 0. So you have a line of equilibria given by 2x plus y equals 0, and furthermore all other solutions are on straight lines, because for example if you divide the two, let's say you divide x prime to y prime and you eliminate the time, so if you do dx over dy, that's going to be 1 over 2. Okay, so that means no matter what the time value is, the solution moves on a straight line. So all trajectories are straight lines on this line of the slope too, right? I mean, if you think about dy over dx as the slope of that line, that's 2, which coincides, by the way, with the eigenvector corresponding to 4. So all solutions move parallel to 1, 2, and if you start on 1 minus 2, you remain there because that's the line of equilibrium. So all solutions on straight lines, because lambda is positive, they will move away from the line of equilibrium. So you have a line of equilibria and all other solutions on straight lines parallel to each other. They have all slope 2, and they move away from the line of equilibria because lambda is positive, the other the non-zero eigenvalue. So you're going to have what is called here a stable line of, an unstable line of equilibrium. Okay, so let's do a little sketch here. Let's do the eigenvector corresponding to 0, 1 minus 2. So x equals 1, y equals minus 2. And through the origin. That's going to be the stable line of equilibrium, right? So again, I'm not going to put any arrow, notice here. There is no arrow on this line. If you start at any point, you're stuck there at that point, because all of these points will make the derivatives, both of them, equal to 0. And all other trajectories are parallel to the line that goes to the points 1, 2. So 1 and 2. So along this direction, you're going to have straight line solutions. So this is how the picture would look like. Wherever you click on a point, except the line of equilibria, you will move on straight lines away from that line of equilibrium. So that being said, case 9, let's do the opposite of this. We'll just mirror the whole picture, the same configuration, but the second, the non-zero eigenvalue will be negative this time. So again, 1, 0 eigenvalue, lambda 1 equals 0, but the second one, let's make it negative. And let's see the default example. I'm going to use the one with the opposite signs like before, just to make the same eigenvalue but with opposite sign. So minus 2, 1, 4 minus 2. And in this case, the solution, if you take the time to compute it, so in this case, lambda 1 would be 0, lambda 2 would be minus 4, less than 0. And your solution in this case will be C1, 1, 2. That's the line of equilibrium, plus C2, 1 minus 2, e to the minus 4t. So let's sketch it here. Line of equilibrium is 1, 2, the one corresponding to 0. All other solutions are parallel to 1 minus 2 and moving toward the line of equilibrium. So 1 minus 2, like that. And all others follow the same pattern. Hope it's not too messy. So in this case, of course, you will have a stable line of equilibrium. And finally, for the 0 eigenvalue, and with that we conclude the real case, that's going to be the double 0 eigenvalue. All right, so double 0 eigenvalue. That's when you have lambda 1 equals lambda 2 equals 0. And so let me show you the example and point out the main difference here. So x prime equals minus 2, 1, minus 4, 2x. And here let's put also the system in component forms to see the difference from the previous one. Minus 2x plus y, y prime minus 4x plus 2y. Okay, so if you compute the characteristic equation, you get lambda squared equals 0. All right, so the trace is 0. Lambda squared minus the trace is 0. Minus 2 plus 2. The determinant is minus 4 plus 4, it's 0. So the characteristic equation is just 0. If you were to, I didn't write the solution here, but if you were to solve it, you will use the second case, right? I mean, when you have to find the generalized eigenvector and all that kind of stuff, right? So the formula for the solution will be the same. let me emphasize here the eigenvector. So for lambda equals 0, the single eigenvector you will get here is going to be 1, 2. And of course, minus 2x plus y equals 0 is the line of equilibrium. Okay, so it's really like before, right? I mean, you can pull out 2 from the second equation and you get this one as well. So you have infinite many equilibrium points. So then why do I take this as a separate case? And why it's not like one of these? I mean, what's different between this and the previous two cases? Well, one thing to notice here is that the solutions themselves are parallel to the eigenvector. If you divide the equations again, so if you do dy over dx, let's start with the second over the first, the factor is actually 2, right? If I pull out 2, let's see if I can have room here, right? So for y prime, if I pull out 2, I get the first equation, right? So dy over dx is 2. And notice that that means these trajectories are parallel to the eigenvector. This is what's different, right? I mean, in the previous case, the trajectories are along the second eigenvector corresponding to the non-zero eigenvalue. And the line of equilibrium is going to be the other eigenvector. Here, both eigenvalues are 0. And it happens here that the trajectories, if you look at the slope of y with respect to x, are going to be on the eigenvector 1, 2. So in this case, basically, the solutions neither move toward the equilibrium line nor away from it. They're parallel to it. That is why this is called a neutrally stable line of equilibrium. Neutrally stable is another name for a situation in which you don't have convergence but nor divergence, so to speak. There is a situation like that in the complex case. But again, I hope the name of the situation is suggestive enough. Neutrally stable, neither moving away nor toward it. So if you run this system, and we will do it, I'll do it, and you should do it as well, you will just see a bunch of parallel lines. The line of equilibrium is in the middle here, 1 and 2. And so again, if you start on this line, you're going to be stuck there. Each point is an equilibrium point. And if you start on any other points, you'll have parallel lines. The direction of motion is dictated by the size of the derivative, and it'll turn as you pass the line of equilibrium. So in this case, it will be this way. This has to do essentially with the derivatives and whether they increase or decrease at that point. And you can prove that the direction changes as you pass over the equilibrium line. But overall, that's what you see. So in fact, actually, when you click on the points here, you can detect the equilibrium line like the boundary between where the arrows change direction. So all parallel lines, you don't move toward the line nor move away from it. You just move on a line parallel to the line of equilibrium. So in general, sometimes if I'm pressed with time when I teach this in the classroom, sometimes I actually skip the zero eigenvalue. But again, these are interesting cases because the geometry is different. And I have to mention also that plotters, which are not exactly that sophisticated, sometimes they don't detect this type of behavior, because in the numerical algorithm they use, zero eigenvalues are really like borderline cases, and the algorithm behind the program sometimes doesn't detect the effect of a zero eigenvalue because they use some sort of approximation, and they don't, the program doesn't detect that, and you may have some misleading pictures because of it. In fact, I think the two plotters I posted on Blackboard, one of them doesn't detect correctly the geometry in the case of a zero eigenvalue. So we're going to finish with a short last part for the complex case. That's much more straightforward because you have only 3 possible behaviors. And then we're going to move on, like I said, with running this example in the computer. So stay tuned for the next part.